I'm really happy to be here at this wonderful conference of this wonderful association, which is an opportunity to meet lots of very interesting people, teachers whom I've enjoyed meeting all through my career. So I'm very thankful to MTA for giving me this opportunity to talk to you, and to the hosts, Azim Premji University, for providing a platform. Okay, so my talk, that's the title. Since in the association meetings, I keep harping on the connection between research and practice. All the skeptics who thought that research is, somewhere else and practice somewhere else told me, why don't you tell us more about this? So I hope to persuade the skeptics in the audience that research is indeed not only useful but necessary to improve mathematics education. And I am particularly thankful that a few of you spoke, because I was beginning to wonder whether there are any teachers attending. One can only recognize familiar faces. So I was very happy to know that there are lots of teachers. So that's great. Because I'm not going to say anything very much new in comparison to what I've said earlier, but maybe putting it together in one place is useful. And I was also told that there will be teachers, so that it's good to share this with the teachers and others working on curriculum, teacher professional development, etc. So that's the outline of my talk. Mathematics education research, what is it? Because we're talking about the meeting points between research and practice. Teaching practice and mathematics education. So I'll say something about how I look at teaching practice. I'm sure it'll resonate with some of your thoughts. Some key research constructs that support teaching. So my talk is organized around this. That's some constructs which have emerged from research and which help particularly make teaching practice more effective, I think. So that support teaching. And these are the constructs that I'll focus on, which seem to be important to me. Noticing children's mathematics. I'll say something about learning also from children's mathematics. Out of school mathematics, then the mathematics of quantity, self-other relation or identity. And so these are the constructs I'll talk about a little bit and give some examples. But of course, there's another area where research has impacted mathematics teaching and learning. That's in the form of curriculum design and so on. So that I'll not focus on that much. It'll only towards the end I'll mention a few things, because I'll focus more on research that's centered around teaching practice and mathematics teaching practice. So let's begin. Mathematics education research, what is it? What do I consider maths education research, so that we know what we are focusing on? There is already a well-organized community of research, math education research internationally. So when we say math education research, there is some reference point. So it's good to, so it's broadly the sort of work that's been done, which is published in journals, presented in conferences, etc., that I have in mind. And this community has a very good representation internationally. So there are lots of researchers from Asia, even from Africa, and of course the West. So the organization of this international community is also very good. It's very strong. It's closely tied to the organization of the International Community of Mathematicians, so which is called ICM. So there's a commission of the ICM called ICMAI, which is for Maths Instruction, International Commission for Mathematics Instruction, and so it's organized under that. I'm not getting into all those details, but this provides a sort of well-defined reference about what mathematics education research is. And there are a number of journals. There are, indexed journals. There are well-known conferences. The community also recognizes good work through awards and so on. Now, where does this research happen? Typically, it happens in, the largest set of institutions where it happens are the teacher education institutions. So it's very close to the work of teacher education. That is pre-service teacher preparation, B.Ed and so on. So colleges across the world which have programs to train teachers or something like B.Ed, offer B.Ed, that's where much of the research happens in universities or in special TEIs, teacher education institutions. And similarly also in India, but my focus is really on the Indian scene. So apart from this, most of my examples and discussion will be from what happens in India. So in India, mathematics education research unfortunately has very little institutional presence as math education research. This is something that we should keep in mind when I speak. So partly my talk is also to suggest that we need more of this, that there's not enough of math education research. And particularly in teacher education institutions, when it's happening across the world, why does it not happen in India? It should. Maybe there are some reasons for that. One of the reasons could be that teacher education institutions have been separate from universities, and it's difficult to do math education research without some inputs from the discipline of mathematics and so on, and without some cross talk between mathematics education at the university level and at the school level, which is why I think MTA is organized in this way, that it provides a platform for this crosstalk between various levels of mathematics teaching. Okay, so there is a lot of research which takes place in departments of education in universities, but that's usually very statistics based, very quantitative research. And in my belief, we can discuss this more in detail. It does not impact practice at all. So it's much of this research is wasted in terms of its impact. Of course, it might help those researchers to grow a little bit, give some experience in statistical techniques, but it's hardly impacts practice. The other kind of research that happens is in specialized institutions. I think Azim Premji is one of them. Homi Bhabha Centre is another. Very few university type research institutions where this happens, and they have built a community of researchers. Some of them young, some of them mid career, some of them older than that, like me. And these are research trends or agendas which have been influenced by the international trends. So they're connected with the international body of research and the community also in many cases. But of course, it's always a challenge to balance this agenda with concerns which are rooted in the Indian context. And I believe that's very important for this community of researchers, that you must always, because after all, math education research is connected with practice. It's a practical, and education is a practical field, so you have to connect it with that. So this is one kind of research, and most of my examples will be drawn from this. Some of those researchers are already present in this room. The other kind of research which is also important is developmental research, which happens largely in the NGO sector. Not many people know about this, but it's hugely important. It's not well known because the documentation doesn't exist. There's not much documentation. But I think, for example, APF would be such an institution where a lot of work is happening in terms of development of resources, development of curriculum material. There's also Eklavya, which has done a lot of work. Similar other institutions that I know about, Navnirmiti is represented here, Jodogyan, and so on. These are just a few examples, but there's a very large number of such institutions, and some of it has percolated and impacted teaching practice, and I'll mention some of that. There's also the possibility of collaborative research between working teachers and researchers or teacher educators. And this holds enormous potential, but it's not really taken off. I think that's one way to go to make sure that research keeps close to practice, and it would be really nice to have more of this kind of collaboration. Okay, that's about research. What do I mean by research, and what do I mean by the practice of teaching? How do I look at teaching? So the first thing to remember is that teaching is complex. It's not recipe-like. So it's not a scripted thing. You don't make a script and you go and just deliver in the classroom. It's hardly going to be effective. It involves, of course, thinking about how you're going to teach, making routines and plans, implementing them. Not only that, the work of actually listening and responding in the classroom. One of the things I greatly enjoyed about math education when I entered this field, I was doing a lot of teaching of young children, and it was so engaging because you have to be attentive all the time to just to be, to find out what's happening. And there are so many different kids all thinking different things and also trying to respond to that. So it's very challenging and it's complex, and it can be very tiring and also rewarding. So getting participation is another challenge in the classroom. Managing uncertainties, unpredictable, unexpected things happen, some response somewhere, some situation, all of that. Taking decisions, creating a classroom culture, and making learning happen. Of course, that's what we all want to do. So each of these things have been talked about by researchers. You can, they've gone into great depth. But this is just to tell you that when we talk about the impact of research on teaching practice, we have to keep this complex activity in mind, and that research can impact in many different ways, and it can, really change teaching in very deep ways also. So, how does research fit into teaching? Uh, I'm talking about meeting points here in terms of what are the real, or practically speaking, which are the places where the twain meet, research and practice. Now, teaching is partly about well practiced routines, but partly also about making decisions in complex situations. It's not like you're making decisions all the time. You often it's just some practice, you're implementing something that you smooth flows smoothly. You're already quite familiar with it, but it also may involves making decisions in certain situations. So you could make decisions while preparing or while responding to students or even while reflecting on what happened and maybe preparing for the future. Now, any complex activity, and this also been studied by researchers in different fields, including management and so on. So any complex field learning happens in and through practice. It doesn't happen in your pre-service education. Pre-service education provides a certain foundation for becoming a teacher, but a teacher really grows, builds her skills and so on in and through practice. And that will happen only when there are opportunities to grow and to learn from practice. So there must be opportunities to reflect. There should be platforms, some leisure time, some interactions, hopefully like this. And then also there must be some opportunities to change. It's not easy to, given the squeeze on the teacher's time, all the kinds of load on the teacher, it's not easy for teachers to change, even if they want to. So, but there must be some occasions, opportunities for change. Okay. So I would say that the research and teaching meeting points are centered around such opportunities to reflect, and the opportunity perhaps to change. Okay, so this is all a little bit of gyan in the beginning, and then we'll go to some examples. Yeah. Uh, so teachers can be supported in their work of teaching by in different ways by through research, and one of the ways is developing certain constructs or certain concepts, if you like. I mean, concepts and constructs are mean roughly the same thing. Concept maybe needs something more out there in the real world, while construct is something more we set up and in order to shape the lenses we use to see reality. So developing constructs that help teachers manage the work of teaching more effectively. So this is what my talk will largely be focused on. Identifying and developing resources and knowledge that are critical to the work of teaching. So also developing this kind of knowledge. A good example is what's called pedagogical content knowledge. Everybody now is familiar with this term, PCK. So as I go along, it'll be centered around constructs, but I'll say a little bit about knowledge and other kinds of resources like specialized knowledge for teaching maths. And of course, there's also certain kind of research which focuses explicitly on developing models for how teachers grow professionally, how teachers change, and so on. So, what are some key research constructs that support the complex work of teaching? Okay. The first thing that I would like you to notice about teaching is noticing. So, this is a important construct. And doesn't seem like a great thing, right? I mean, all of you would have thought of it at some point or the other. But it's somehow, when I went back and checked the PhD thesis which have come out of Homi Bhabha Centre in Math Education, three or four of them I find, discuss this concept of noticing. So it's been very important also in talking to some of my former students, that noticing is a concept that's actually helped them organize their whole perspective, or change their perspective to math education. So, what do teachers notice? This notion was introduced by John Mason. In fact, I made this slide much before I knew that Mason was coming and going to give a talk. He's doing that, right? Yeah. So that's just great. So he introduced this notion, and he called it a discipline of noticing, and spoke about how one can develop this aspect of noticing in a teacher in different ways. Systematic reflection, preparing with the imagination, recognizing choices, labeling salient events and actions. And hopefully, I don't know if you're going to hear it from him, but if you don't hear tomorrow or so, I think when John Mason speaks, maybe you can go and read up some of his work. Of course, I've taken this from, so as I go along, I'll mention some people who have done their PhDs or research at Homi Bhabha Centre. That's from Jayashree Subramaniam, who's also here. Okay, what are the okay? So noticing what is going on in the classroom, and that's not very easy. And there are some factors which shape this noticing by a teacher. What are these factors? Of course, one is the teacher's own goals. What does the teacher really want to accomplish? And these goals can be quite different. It can be just finishing something in the syllabus, making sure the students learn that, or it can be something like developing students' reasoning, students' interest towards mathematics, getting them excited, or various goals. And of course, there are various beliefs that teachers have. One of the beliefs that many people have talked about is that teachers think that students cannot do problems on their own unless they're taught the method to solve the problem. That's actually not really true, and it comes as a surprise when they find that students actually do something on their own. Okay, but today I'm going to talk more about the things that I've circled. One is that notion of children's mathematics, which I already mentioned, and maybe some examples that read content knowledge. And I'm going to talk a little bit about this interesting relationship between the teacher, the student, or the students as a whole, and mathematics. Right? It's a sort of triangle and important relationship, and I'll talk a little bit about that. So that's my first example. All my examples I've taken from work done by others at Homi Bhabha Centre, which I've been partly involved in. So why are there no ones? Maybe some of you have heard this example before, but it's worth. Any guesses what it's about? One-its? Decimal numbers, right? Okay. So this is from classroom teaching, class 6. And that's a decimal number in front of you, 683.683.12. Of course, you can see the place values, hundreds, tens, ones. Then there's a decimal point, and then there's tenths and hundreds. And this research is by Shika, who is also here, Shika Tucker. So what happened was this in the classroom. The teacher was talking about introducing decimal numbers after talking about whole numbers, saying like you have place values in whole numbers. Just like that, you have place values after the decimal point also. And there are tens, and then you have tenths, you have hundreds, and so you have hundreds, and so on. So naturally, a student pipes up and asks, so what about one-its? So student 1 says one-its, and student 2 says one-its nahi hota, chal. So this is a conversation that Shikha, who's sitting in the class, notices. But the teacher, it's not clear whether the teacher noticed it or did not notice it. But there's no response from the teacher. The teacher just moves on and goes to the next. The funny thing is that if I'm saying something which my memory is distorted. Shikha will correct me. But she observed, I think, about 8 classes, and this decimals were taught in almost all of them. 4 different teachers, 8 classes. I think it cropped up in this question came up in like 6 out of those 8 classes. So it's a very common thing, and it's sort of expected. It's interesting to know why it comes up, and what how to deal with it. Now, year 2, in the same teacher's class, the same thing happens. So, student 1 says, "Ma'am, वनच क्यों नहीं होता है?" So, this time the teacher catches it. Right? She picks it up and she says, "Nikita is asking why is vanaths not there?" So, she puts it back to the class. I think there's a term, there's a label for this, revoicing or something like that. You revoice what's happening. And it's also an interesting concept. So, students 2 says, "Ma'am, hota hai." So now the students, of course, they quickly change, right? They adapt to what the teacher is telling you. And so they said, "Hota hai." And then there's a discussion which ensues. We'll leave the discussion for a bit and look at why this question comes about. How do we analyze or understand this? So that's the student's question. Why is there no distinct place for vanaths? And our questions are, why are the students asking this? And is it important to respond in detail? Those are our questions as we reflect on this episode. Now, to understand the students' thinking, we need to draw on 2 kinds of knowledge. At least this is the sort of analysis that Shikha offers. I agree with that. A part of the knowledge is mathematical, and a part of the knowledge is about the way students think. So it's what is called, in teacher education, in the standard traditional approach, it was assumed that content knowledge is all known and what you need is only pedagogy. And so you're taught pedagogical techniques like methods, and you take some concept or content and you package it in that material and you go and do your practice teaching. So this is how teachers are prepared. Now that approach was challenged very radically in a very important way by the work of somebody called Schulman in the 70s, I think. 80s, sorry. So he said that what you need is actually a kind of knowledge which amalgamates, which ties together content and pedagogy. They cannot really be divorced from each other. So he called it, he introduced this term, pedagogical content knowledge, and now it's found its way into all the syllabi of teacher education. I think the moment you come into APU, you're taught PCK, and till you leave, you should keep repeating it, I think. So that's, anyway. So PCK is a big thing, right? So let's look at what's the PCK involved in this example. So one of the things which is happening is that what's called a kind of mirror idea, mirror metaphor, if you like. The mirror is placed on the decimal point because the teachers kind of induce that mirror metaphor, right? Because she talked about tens and tenths, hundreds and hundreds. So, if there's ones, then where's oneths? So it's a sort of, there seems to be a missing oneths, and because the mirror is kept on the decimal point. Now, this raises an interesting mathematical question. So, what really is the decimal point doing there? And where is the point of symmetry or the mirror? Where is it all reflected? So, this becomes clear when you look at the mathematical representation, right? And you see, for instance, we can write the place values in terms of powers of 10. And you see that tens are 10 to the power 1, hundreds 10 to the power 2, 10 to the power 3, and so on. On the other side, you have 10 to the minus 1, 10 to the minus 2, minus. So where is actually the point of symmetry? It's on the units place. It's not on the decimal point. It's 10 to the power 0, the ones. So the units is the anchoring place value, so to speak, in the whole numeral representation of digits. And this is something very important. That every place value refers back to the unit. So the notion of unit is very central, somewhere missing from the discourse of teaching and learning. So, so that unit is the crucial one, and that's where. Okay, so this gives us some insight into what's happening mathematically and why the children are sort of tempted to think about the decimal point as being something of mathematical significance. It's not. It's just a convention to show where the units places. One could as well put the decimal point on top or below, or just to mark where the units places. Right? That's its function. Of course, when you actually deal with things in the classroom, uh, it's not like you tell the students, "Oh, look, it's not look at all the 10 powers, 0, etc." That's really, no, that's not what you do in the classroom, right? It's not giving GAN to the students. It's rather letting something emerge from the classroom, and that's what happened. It's very interesting. So what actually happened in the classroom was the teacher did not deal with the student's question in the first year. In the second year, the teacher posed the question back to the students. We saw that. And the students had their own way of explaining why there are no ones. So one of them said, suppose there are ones. And then put that, say let's say there are 7 ones. And they know that 7 ones would be written as 7 by 1, 7 over 1. Because 1/10 would be written as 1 over 10, 200s would be written as 2 over hundreds, and so on. So this would be 7 over. And that's the same as 7 ones. And so it would be back. So there's no separate place for one-its because one-its are the same as one. This is one of the arguments. There's another interesting argument also, which now I don't recall, but it's there in that reference and you can look it up. I think it's should be available. And I have not put a list of references at the end, but I put them on slides. You can find them. If you don't find them, you can always write to me or Shikha. So let me go to the next construct that I want to talk about. Children's mathematics. So, I mean, noticing is a huge thing, and there are many things connected with it. And one of the things is what is the sort of PCK that the teachers already imbibed or reflected on and gained. And so that's going to impact what the teacher notices. In fact, the part of the research had to do with the difference between what the teacher's response was in the first year and in the second year. Because in between, we did a lot of workshops with the teacher, focusing largely on PCK. Of course, it's only a hypothesis that maybe that helped the teacher notice certain things. We can't prove that. But the belief is that it does, so somewhere about these things. And in fact, we were also quite surprised that this whole business of this mirror metaphor and so on has been reported in the research literature. So it's to be expected and does crop up in the classroom. Something we, after looking at what happened in the classroom, we became. Okay. The other notion that's been quite influential is the idea of children's mathematics. And this one comes from, I think all of you have heard the name Piaget, right? Piaget was a very famous cognitive psychologist who threw up some very surprising findings about the way children think. And that led to the education community recognizing that, we never expected children would think like this. And so it has a great implication for teaching and learning. And many very well-motivated mathematics educators who later became famous went to work with Piaget. One of them, I don't know how many of you have heard of this name. Have you heard of the Logo program, which, the turtle moving around and so on, Papert? So Papert was one of them who went and actually worked with Piaget. Many, Vergnaud in France, there were some researchers who went to the US, and then there was a whole group which formed in the US called the Cognitively Guided Instruction, CGI studies, and so on. So the idea of children's mathematics came directly from those groups working on how children think about mathematics. And it's also called by, it's close to the what's called constructivism also, and so on. I mean, there are different names for it, but I find this the most evocative, children's mathematics. So children's problem-solving approaches and strategies can be very different from conventional ones. Often they have a strong underlying logic and mathematical reasoning, And even what appears as errors can have an underlying logic. And so I'll discuss a couple of examples a little later about so called errors and underlying logic. But let's look at something of children's mathematics. Okay, this is a example I'm taking from another bit of work done in Homi Bhabha Centre. And this example is titled Purmeya Calculate Pandaramis. Just, let me calculate patiently, just allow me to do my thing. That's okay. So the task which was given to a student, Selvam, it's a pseudonym, I mean, it's a different name, Selvam was doing this task. So he finds that 50 by 150 somehow he figures out is 3 by 2. Now, he doesn't know how to interpret 3 by 2 first. He thinks it's three full things and two something or some. Then the teacher has to help a bit, and he realizes that it's the same as 1.5. So the idea is to find out, what is if it's 1.5, then how do you find the percentage of 50 over 150, right? So that it's actually 150 by 50. So that's a typo there. So he figures out that 2% of 150 is 3, right? Yeah, because 1% is 1.5. Right, so that's how he figures. He's able to work that out. 1% is 1.5 of 150, and so 2% of 150 will be 3. He figures that out. Then he continues in this way and finds that 4% is 6, and then 6% is 9, and so on. So he just goes stepwise. Now the teacher is getting a bit impatient. Yeah, the teacher says that, okay, now that you know that you double from 1.5 to 3, and 1% to 2%. So why don't you try doubling from 2% to 4 and go from 3 to 6, and then 4 to 8, and so it'll be much faster. So no. He says he declines this help. He says, let me do it, Purmeya calculate. So he says, so he went on adding in steps of 2 till he reached 32%, which is 48, and 34%, which is 51. And so he says that 50 is a little less than 34% of 150, which is perfectly correct, though not exact. Right? He didn't arrive at that fraction. Okay, so that's from Sri Subramaniam's work. Now, what I want to point out is that, see, this fondness for addition, often among students who we think are weak, they're very comfortable with this, and they in fact love doing this. This is from another student many, many years ago, from some work done at the Homi Bhabha Centre, in which I was involved, called Aman. And like I said, it's like really long time. So he was calculating the price of some 1 packet, 2 packets of flower pots, and he just went on adding. I mean, it's not even like he added to the previous number, right? He started from, he just wrote many 52s, and he loved to add it. And it's full of addition, so the next page is you can just see that it's all absolutely correct. He loves, I think, this carryover and doing it correctly. And so he did this. Now, this is a big resource for many children, and it's interesting to ask, like, what is it why do they find such comfort in addition? Of course, it's not effective. It's going to, they're going to stumble if they have to learn mathematics further, and they have to get over this. But it's important to acknowledge that this is a resource and a strength on which they can draw in order to make further progress. And this is a very interesting story about Selvam, which is, I think, there in, it's going to be, I think it's a manuscript we have submitted, and it's hopefully will come out, and you'll read more about that story, about, Selvam's owning that mathematics, and the teacher acknowledging that. So we think of it as, there's the teacher's mathematics, and then there's the student's mathematics. And the student's mathematics, we say it's the student's because the student in some sense owns it. That's his. And you're trying to invite him to come over to your mathematics. So there's a certain distance that has to be traversed between the teacher's mathematics and the student's mathematics. And this sort of recalls that triangular relationship between the teacher, the student, and the mathematics. Right? And it's not just that it's a question of knowing some techniques and so on. There's also this concept of identity, which I'll come to later. Somehow, and the notion of ownership has to do with that. So there's a sense of owning that. And there's maybe a feeling that some of the mathematics that's discussed in the classroom is not, I don't identify with it. It's too distant from me. Okay. Now, I want to, so children's mathematics is not only something about making space, listening, noticing, and so on, but it's also something that we can learn from. And this is, hopefully, we'll come through with this example. And the example I'm talking about is adding fractions. Yeah, this is also something that you notice children doing. And we put it in, I'm going to pose it to you in the way we pose it in our teacher workshops sometimes. And I'm going to look forward to your response. So, this is the task. A student in the class had added fractions like this. 3 by 7 plus 2 by 3 is 5 by 10. Of course, that's wrong. I should have put a star there. So, added the numerators and the denominators. And so, why do you think students add in this way? The next para says, when the teacher asked the student why she had done it in this way, the student said that her father had taught her. This is all fictional. The teacher explained that this method was wrong. On the following day, there was a complaint from the father. He pointed out that the teacher had added exactly like his method. This was his example. Marks in history, 35 by 50. Marks in geography, 24 by 50. Total marks in social studies, 35 by 50 plus 24 by 50, which is 59 by 100. So the challenge is for you, how would you respond to the parents' criticism? So if this were a workshop, I'd give you like lots more time to think about this and then to listen to each other, and you'll find something very interesting that people are thinking and saying. But we'll sort of bypass that. And notice that, so this is not fraction addition, we know that. But it's an important binary operation we do with fractions. And it's, of course, the notion of equivalent fractions doesn't apply here because you will get different values if the denominators are different. And this is something like taking the average. It's a sort of weighted average. If you had more weightage for history, say, compared to geography, you would say 60, and then that would get more weighted. So it's not just a simple average, but it's taking like a weighted average. So it's a different sort of operation. And thinking about it more carefully, you discover something which is an important theorem. And this is the theorem. So say A by B is a fraction, C by D is another fraction, and they're not equal, they're unequal. Then the fraction A plus C over B plus D is in between them. Is always in between. If C by D is greater, then this is greater than A by B. If C by D is smaller, then this is smaller than C by D. Smaller than A by B. So it always lies in between. So it's a very interesting theorem, and children already, this intuitively, because if your performance is very good in history and not so good in geography, your overall performance is somewhere in between. Right? So there's many, many situations in which this sort of reasoning applies. And I'm going to give you another strange example, which we sort of discovered in the process of doing all this work. It is that comparing shares. Because this by itself is very interesting, which is that you can always write down the share, when 2 rotis are shared equally among 3 children, the share of each is simply 2 by 3. So when m rotis are shared among n children, each one share is m by n. You can just write. That's because the fraction notation is actually a notation for division, for the division result of the division operation. So you can straight away write it. So now you can also use this to compare these fractions in a very interesting way. So let me show you this argument. So let's take 2 by 3 and 3 by 4. Which is bigger? So what we do is we put a line there. And then you see the 3 by 4 group is divided into two subgroups. One subgroup gets exactly the same as the one on the left. And the subgroup which is left out, which is one roti and one, gets more. So if everyone's got to get equally, that person who gets more has to share something with the others. And then everybody ends up getting more. Right? So therefore 3 by 4 is bigger than 2 by 3. Right? It's quite interesting. And the reason for this is that you can express 3 by 4 as 2 plus 1 by 3 plus 1. So it's like comparing 2 by 3 and 1 by 1. And 3 by 4 is exactly in between those two fractions. It's the same thing that we saw earlier. And the same thing works also here, 3 by 5. You divide it into two subgroups. The one on the left gets exactly the same as the 2 by 3 above. The one on the right gets a little less, because 2 by 3 would mean, so what is it? So if, you can apply the same thing actually, divide them further into subgroups, one which is 1 by 2 and so on, and compare it. So the 1 by 2 is actually less than 3 by 5. So you can see that, if you take halves, there's a half left over. And so there are many ways of showing that 3 by 5 is more than 1 by 2. And therefore, they get a little less, the other subgroup. So these people who've got more, the 2 by 3 subgroup, has to share a bit of what they've got with the others. And then so everybody gets a little less than 2 by 3. So this is, it's the same argument again. 3 by 5 you express as 2 plus 1 by 3 by plus 2. And so it's in between 2 by 3 and 1 by 2. So you can, in fact, think of it as a theorem. So when two subgroups hold different equal shares, equalization will need taking from the greater and giving it to the smaller. And so this is the same thing that works. And there are many situations which involve ratios, comparing ratios, etc., which work like this. And it can be quite powerful in learning fractions. Okay, so we can skip this. I think it's just the same thing. Okay, now this is something that we learned from an example of children's mathematics, going deeper into it and finding some mathematics behind it. I want to show you another one, which is this example of measuring length, which is taken from work done by this organization called Educational Initiatives, which does a lot of testing, large-scale testing. It's also an important kind of research, and some of it has been published. And it's good to keep in mind that, like I mentioned earlier, that this research also happens in the NGO, sometimes commercial organization sector, but it's important to take that on board. Okay. So this was the question given to children, and it's about what is the length of this pencil. Now, we think length measurement is pretty straightforward, and nobody should have a problem with that. But it was very surprising to find children's responses. And here, of course, it's done in a non-standard way. If you do it in a standard way, you'll get a standard response. It's interesting things to begin to happen when you do it in non-standard ways. One of them is to give a broken scale, which doesn't have the left part. Another is to give this, to shift it and give. So, which option do you think most young students will choose? 7. Okay, 7 is okay. And the correct answer would be? Is what? 5, right? 5. Yeah. Okay. So some might choose 7. So, and the correct one is, so we should, between 5 and 7, you should exhaust the options, right? Okay. So option B is the correct one. Not many kids have chosen that. Like you guessed, option D is the most common response, which is the incorrect one, which 42% have chosen. This is a very big sample, so it's statistically quite reliable. Option C is also chosen. Option A is also chosen. So what can be the reasoning behind this? Yeah, yeah. Yes, but how much? Is it arbitrary? Why did they choose those particular? Okay, so there's a kind of approximation, but let's see. Maybe the children are doing something quite precise. So I want you to watch this video. Okay, so we all think measurement is very simple. So let's watch this.
Let
Do you know how to measure length? Slightly dopey.
the pencil point is on C 6 centimeter. That's why I think it is C, the correct answer. That is tell the point reaches to 6. So I can that it would be 6 seconds. There is 1 centimeter here, 1 centimeter here, and 1 centimeter here, 1 centimeter here, and 1 centimeter here. If you add all these, then the answer will come 5. Actually, it's 5 centimeter, but it is a little long. It should start from here. So it becomes 5 centimeter. This point is touching to the 9. That's why it should be deep 9 centimeter.
Yes.
The pencil is showing 6 centimeters because the 6 centimeters, the point 6 centimeters is matching, that's why.
Okay.
1, 2, 3, 4, 3,
So you pumped that and that's why it's written A. And now because this point is A.
No. I'm starting from here. So 1, 2, 3, 4, 5, 6, 7, 8, 9.
This point will count as 1 and then 9 will be 6. This is 1, 2, 3, 4, 5, 6. Let's see how much picture there is.
Start from 6, people. It start from 4, 4, 1, 1, 2, 3, 4, 5, 6. And the answer is 6 because it's starting from here. 1, 2, 3, 4, 5, 6 is and the ending point is here.
Is this point 1 centimeter or is this much 1 centimeter or is this much 1 centimeter?
I think this point is this to this is 1 centimeter.
This to this is 10.
Yeah.
And this to this?
That is 0 centimeter.
This is 0 centimeter. How much is this to this?
2 centimeters.
Okay, so this much is 2 centimeter?
No, yeah.
Okay, how much is this?
Five centimeters.
Only this much is 5 centimeter? Or you're counting from all the way?
From here there, but the pencil doesn't start from there. But still, these markings means this is 1 centimeter, this is 2 centimeter, this is 3 centimeter. It ends up to 6, so I feel it's 6.
Okay, so you're saying that because the anywhere 6 centimeter must be 6 centimeter.
Yeah.
Okay, fine. So tell me, what is 1 centimeter on the scale? We put in 2 fingers. So how much exactly? Okay, so you're saying this line to this line. That is 1 centimeter. Is that what you say?
Yes, sir.
Okay. That was a sort of clipped version. It's there on YouTube somewhere. If you want, you can look at it in greater detail. Somewhat surprising, isn't it? Huh? And it's not that the children are quite articulate and they have some sound reasoning for why they say. It's just that they're totally unaware of how measurement works. What is the scale hides is the way measurement is actually done and constructed and hidden inside the scale. Right? The scale is like if you read an ammeter or voltmeter or something, you'll just read the number off, right? You're not going to bother about how it works. It's in some sense, it's exactly the same here. Okay, we're back to the slide. So I leave you with this. I'll not discuss a lot. But the interesting thing is that just maybe this one slide. So there are two kinds of errors. Of course, one is that, look at the endpoint and the other is to count the lines. And surprisingly, one of those errors, right, comes down with age. There's class 4, class 6, class 8, comes down. The other correct answer, which is green, goes up. No problem. The surprising thing is the counting lines error. It stays almost flat. Right? It persists even among the high class. So it's something to think about. I discuss this with students. They're like, why is the 6 centimeter error so persistent? And there is a mathematical reason because it even works if you count the lines to some extent. You can do comparisons of length because they're equally spaced. If you do it in a systematic way. But what doesn't work is operations, addition, subtraction, multiplication, and so on. So we'll not discuss that in great detail because we're running out of time. So which tells you that measurement systems must not only work for comparison, it must work also for joining, taking away, multiplying, and so on. So which all correspond, the real operations correspond to certain mathematical operations, and there must be a one-to-one correspondence and it should work. Okay. Out of school mathematics. So, there's a lot of talk about this, I think, recently because some things were published. There's a famous example of calculating with coconuts. What's the price of 10 coconuts if one coconut costs 35 rupees? And it's very easy for you because you just put a zero at the end, right, and say it's 350 rupees. But that's not the way people do it generally. So I'll skip this again. So one tribal adult from Bihar solved it this way that 3 coconuts cost 105 and so 9 cost 315 and one more is, so that's 350. It's this from the work of Arindam Bose, who's also here. And if you think about it, you see, this is not very obvious why we place a zero at the end. It's because when you place the zero, the place positions get kicked up by 1 and so each value goes up by 10, so 10 times, and so that's really the reason. Okay, so I'll skip this again and I'll skip this as well. It's a famous division problem again from Arindam Bose's work. Okay, let me say a little bit about this. And you see, when we talk about children's mathematics, in fact, in the old paper which looked at that coconuts example from Brazil, which is from the 80s or 70s? 80s, okay. And keep getting confused. So, Teresina Nunes, the main author of that paper, she says that maybe the children are thinking about some abstract coconuts or quantities. What they're manipulating is, coconuts on the one side and prices on the other. It's not like they're not pushing symbols. So there's a big difference between working with symbols, symbolic mathematics, and the way we work with numbers and so on, and thinking about quantities actually. And so I think it's important to remember that when we teach numbers, we're teaching quantities, and to bring that in as much as possible. There's another example where these are kids from, I think, 4th grade, and they are, they figured out that 145 minus 100 is 45. They know that. Then the teacher asked, what is 145 minus 98? Now 100's gone down a bit. So does that mean your answer goes down or does it go up? Children are, so there's a big debate in the classroom. So is it 43 or 47? Then one kid says, like you've got this big thing to take away and then you have a littler thing to take away. So you have more left. So this is typical thinking about quantities. It's not about numbers, and it's abstract. So we tried to do some work on this, me and my collaborator, Christine Chambers, to develop some kind of an idea of quantity. It's still work in progress, but we have a couple of papers out. And so I thought I'll just mention that. So let me also not dwell on this. The other important thing I, talked about is this self-other relation, the construct of identity. We talked about ownership of mathematics. The children's mathematics, not just in a cognitive sense of what the children know or comfortable with, but what also they identify with. This notion of identity, sort of came into math education literature as a way of accounting for what are called affective factors. How involved or engaged the student is with the mathematics. Does he find or she find joy in it? Does it put him off? It's a very important thing for teachers, therefore, to be aware of. This was one famous example that, these are high school students, black students, I think, or Hispanics, I don't remember now. Work of Nasir from Harvard, I think, US, I forget. So if you pose the example in terms of school mathematics, you get some absurd answers that they just don't even attempt. But you pose it in the context of basketball, which they all play, they just get it. So it's the mathematics they identify with. It's their mathematics. They own it in some way. It's close to them. And so, the teacher's effort is to bridge this distance and to traverse that distance. Okay. Of course, when we talk about identity, it's also connected with this, I think there's a nice way of interpreting it as the relationship between self and the other. And the other being sometimes, it could be the student and the teacher, or it could be the student and the mathematics, or it could be the teacher and the student. So that's why the triangular relation is. But there's a kind of othering which happens, which is sort of marginalization. So you push out the other, and the mathematics works in that way. It can also be a gatekeeper. It can push students out. When they don't identify with the teacher's mathematics, the teacher sees the distance. So this is again something very important. A huge amount of literature is focused on this. I have not gone into it in great detail, but there are many others, who have worked more on this. I think Jayashree has not come, but she's one. But there are several others who could speak much more on this, on this tendency of mathematics to other the student, to push him or her out, to deny opportunities, to sort of work as a gatekeeper. Okay, so that kind of brings me to more or less the end of what I wanted to say. I'll just run through these slides because I wanted to remind you, not only the work of teaching, but there are many good things which have come out of math education research, developmental research, which have entered the curriculum design and made it much more effective. So I'll just mention some of them. They're not. So one is this, what's called the empty number line. By the way, some of these things have come into the new NCERT textbooks as well, which is a good thing. This came into the older set of textbooks, which is the partial quotient division. Some interesting stories. Look up Shikha's paper on this, very interesting. This is even older, and I took that from the recent NCERT Class 4 textbook. But there's, of course, an important role that the spike abacus plays, which the Dean's blocks doesn't, which also is good to remember. Many other powerful representations like the bar model. We saw fractions through equal sharing contexts. Two colored tokens for integer addition and subtraction, the vertical number line for integer. Many of these things have come into the NCERT textbooks. Some of them which need to be researched and worked on more, I think, are double number line for proportion problems, the multiplication operator diagrams, which I don't find much of it, but it's very promising. And then there's very interesting work done by Raki on the additive blocks in symbolic expressions, how sort of marking them off and thinking and reasoning about them actually improves the learning of algebra. Some of it is also found its way in the textbook, I think. Okay, and I want to acknowledge all these wonderful colleagues of mine at the Homi Bhabha Centre. Not all of them are here. I wish they were, but some of them are, and that's a very happy thing. And of course, I acknowledge HBC TIFR, which has been a wonderful institution for doing this kind of work. And I hope more such institutions come up and grow. Yeah. Thank you.